Hi, my name is Thomas Rosenstatter and I present the work I've done together with Tomas Olovsson and Magnus Almgren from the Chalmers University in Gothenburg, Sweden. Our work is named V2C, a trust-based vehicle-to-cloud anomaly detection framework for automotive systems. And this work focuses on how we can make use of trust and reputation models in order to identify anomalies on a fleet level. In order to get started, I will first give a brief overview of our work, and then I will continue with the attacks and anomalies that such a framework needs to be able to detect, and then I will go into more detail of our framework. In summary, we focus on how we can identify anomalies only by observing surrounding or incorporating vehicles in the first step. Then, we further look for more information about these anomalies on a fleet level by also using the data that is available in the vehicle cloud. We first identify 3 attack scenarios or anomaly scenarios which such a framework needs to be able to detect. Second, we define the requirements as well as suitable approaches for each of the 4 modules that our framework consists of. We also look closer into these specific approaches and techniques and evaluate them for each module separately. Lastly, we discuss how this framework can be used based on a more detailed use case. In this presentation, I will focus on the framework and some of the identified anomalies. So please have a look into our paper if you need more details about the approaches that we have analyzed. How does the proposed structure for this framework look like? We have 4 modules in our framework, and the first module is located in the vehicles themselves. The aim is that these vehicles evaluate and assess each other based on the interactions and the observed behavior, which results in a so-called trust score, which is a number between 0 and 1. And this number indicates how reliable the other vehicle is. For instance, in this case, vehicle 3 computes 3 trust scores. It computes a trust score about vehicle 1, a trust score about vehicle 2, and it also computes a trust score for itself. Of course, the own evaluation has its limitations and is biased, but it might be still necessary and valuable when further investigating what's going on. This self-evaluation or these trust scores are then uploaded to the vehicle cloud and in module 2 aggregated to 1 trust score per vehicle. So we have the aggregation of the trust scores about vehicle 1 that have been perceived by vehicle 2 and vehicle 3. And once we've aggregated these trust scores, we further observe in module 4 how these trust scores develop over time. And as soon as a change is detected, that there is some behavior that looks like an anomaly, we further trigger the cloud analysis. So in the cloud analysis, we first try to find anomalies of this specific vehicle by using the data we have in the cloud. And next, we also try to find similar patterns in the entire vehicle fleet in order to identify the problems that happen. Before we continue to the 3 attack and anomaly scenarios that we have identified, we just want to highlight that we consider attacks and anomalies that change the vehicle's behavior in a more subtle way. Of course, we need to have an in-vehicle intrusion detection system as well as prevention techniques in the vehicle in place in order to detect and prevent immediate dangers. Now we give a few examples of the 3 attack or anomaly scenarios that we consider in this work. So scenario 1 is unauthorized firmware manipulation, and an example for this could be an attacker or the owner who sends wrong modified warning messages to the other vehicles in order to reroute them through another route. Another example could be that the owner of the vehicle wants to drive faster than the legal speed limit for cases when the speed is limited by the vehicle itself. Second, we have hardware and software failures that can lead to a change in the behavior and possibly also to a violation of safety requirements. So like in this case, the camera experiences a hardware fault and therefore cannot measure the distance to the vehicle in front properly and drives far too close to the vehicle. This behavior can be observed by the other vehicles and also be reported in form of a trust score. Lastly, we look into legitimate software and hardware updates for a specific module in the vehicle. Due to the fact that vehicles have a big variety of different configurations, it may be possible that not all possibilities have been covered through test cases. Therefore, for instance, another ECU, a microcontroller in the vehicle, may be affected, and this could lead, for instance, to the vehicle driving too fast in certain road conditions because the road condition of heavy rain or slippery road is not correctly identified. And this can be also detected or has to be detected by our framework. I will now describe the framework in more detail based on a use case. We simulated 3 changes. The first change is an immediate drop of 0.1. The second one is an immediate increase by 0.2. And the third change is more subtle. So this change is similar to the last use case or last scenario that I have described, where a certain misbehavior is only perceived in certain situations. So here, more and more vehicles are reporting each day that there is a drop in the trust of 0.05. And this could be, for instance, due to the vehicle driving too fast when the road is slippery, so only in certain situations. Now we can start with the modules. So module number 1 is in the vehicle, it's about the trust and reputation. So the aim is that we perform a peer evaluation, which ultimately computes a score describing how reliable the other vehicles are, or in other words, how much trust we can have in the other vehicles. So the focus here is detecting a change in behavior and reflecting this in form of a trust score. Therefore, we first investigated existing methods around trust and reputation. So these trust and reputation models need to evaluate and assess other vehicles based on the interactions with them and the information received via vehicle-to-vehicle communication. We've identified the need for 2 trust scores. So we have TIII, which is the trust score of the own vehicle. So it's the self-assessment. And TIIJ, which is more important because here we have the notion of the peer assessment. We have individual vehicles assessing each other based on the experiences they had when driving with each other. And this is reflected in TIIJ, which is the trust score computed by vehicle I about vehicle J. Additionally, we also recommend to include a confidence value. So this confidence value should reflect how long the interactions with a certain vehicle has lasted. For instance, if a vehicle has been only communicating and being assessed for a few minutes when crossing an intersection, is less valuable than a vehicle that has been platooning or driving and interacting with a specific vehicle over a longer period of time. And overall, in the end of the day, we submit these trust scores to the cloud together with the confidence value. So here we recommend, for instance, a period of every day. Once we receive the trust scores for a certain period, we can aggregate them in module 2. There are several ways to combine the trust scores reported by the vehicles. The most apparent way is to use the arithmetic or geometric mean to aggregate the trust scores. Another approach, sometimes proposed in trust and reputation models, is the use of Dempster-Shafer theory, or more specifically Dempster's rule of combination, in order to model the uncertainty of information or the evidence received. So here, models, for instance, use Dempster-Shafer theory in order to answer the question about a certain warning message received. Like, is this road indeed slippery? And then we model the degree of belief and come to a conclusion with a certain certainty whether to trust or distrust this information. For our framework, however, we do not want to make a decision whether we can trust or distrust a certain vehicle. We want to have a more fine-grained information about how the behavior has developed over time. And for this reason, we believe that the mean is the most applicable solution. The third module is the detection of a change in the observed thrust score per vehicle. Here we need to observe the combined thrust score per vehicle, which is reported, for instance, every day, and we need to decide whether the vehicle's behavior has changed or not. Observing the mean and raise an alert when a certain threshold is exceeded is, however, not sufficient, as it would take too long to identify that a change has occurred. Therefore, we investigated solutions with the focus on resource requirements as well as reaction time and found two candidates that fit our use case, namely cumulative sum and Bayesian change detection. Based on our simulation, where we have three changes, change number 1 being an immediate decrease by 0.1, change number 2, the immediate increase by 0.2, and change number 3, which is a slow decrease by 0.05, where each day more vehicles report a lower thrust score by 0.05. In this comparison, you can see that both detection techniques identify that a change has happened. However, Bayesian change detection is much faster and already identified change number 3 when 3 out of 9 vehicles have reported a lower thrust score of 0.05. Furthermore, QSUM is also computationally more complex than Bayesian change detection and therefore requires more resources. And for this reason, we recommend using techniques such as the Bayesian change detection for identifying a change in the thrust scores in module number 3. The last module, module number 4, is responsible for analyzing the data in the cloud and finding patterns of anomalies on a fleet level. For scalability reasons, we recommend to first only analyze data related to the vehicle which triggered the alert due to a change in its behavior using the peer assessment. Once the anomalies also have been identified in the cloud data, we can further look for similar patterns in the entire vehicle fleet in order to know how many vehicles in our fleet are actually affected. The data in the cloud strongly depends on the stakeholders. For instance, an OEM uses its infrastructure to perform remote updates, remote diagnostics, but also wants to provide customers with convenient services, such as remote unlock and the ability to see recent trip statistics and the charging status on the mobile phones. Depending on this available data, we first need to perform manual investigations in order to identify and adapt specific techniques. And for this reason, we propose to use specification-based anomaly detection to cover violations or anomalies in regards to the application layer protocols that are in use, but also in regards to other specifications, such as the expected regions based on the IP address. And further, we recommend to follow a process such as KDD, knowledge discovery in databases, when looking for suitable machine learning techniques in order to adapt them for our use in this framework. And once we have identified these techniques, we can further work on automating this process in order to be faster in identifying the anomalies on a fleet level. In summary, our proposed framework should be seen as an addition to existing in-vehicle detection and prevention techniques, as we focus on anomalies and attacks that cause only subtle changes and can be identified by the surrounding vehicles, using this peer assessment rather than only evaluating the own system state. As for future work, we want to verify this framework in a more holistic simulation in order to be able to analyze it in more detail. And with this said, thanks for listening, and I will be available for questions in the live Q&A. Thank you.